everyone. I welcome you in the discussion of unit second of pharmaceutical organic chemistry second, that is called BP 401T. Myself Dr. Sandeep Kumar Bansal, professor at Ramesh Institute of Vocational and Technical Education, Greater Noida. If we talk about unit second of this subject, it is divided in 4 parts. Part 1 deals with the geometrical isomerism and part 2 deals with the conformational isomerism. In geometrical isomerism, we have to see the various methods for the nomenclature of the geometrical isomerism, isomers like cis, trans, Ez and syn and anti system. Simultaneously, we have to see the various methods that are used for the determination of configuration of geometrical isomers. In part 2, we have to study about the conformational isomerism and with reference to ethane, N-butane and cyclohexane. In part 3, we have to go for discussion stereoisomerism in biphenyl compounds, that is called atrope isomerism, and what conditions are required for optical activity, means how biphenyl compounds exhibit atrope isomerism, what conditions are required, that we have to see in this part. And in part 4, we have to go for stereospecific and stereoselective reactions. So, now we have to recap the part what we have discussed in our previous lecture. In our previous lecture, we have seen that the compounds alkene shows this type of geometrical isomerism and alkenes are the example or the compounds that exhibit geometrical isomerism. So, the conditions that is supposed to be fulfilled by any geometrical isomer is, first is unrestricted rotation, and the second condition that is the substituents that are present around this double bond. Now, if we talk about this 2 carbons, let us designate this carbon 1 and this is carbon number 2. So, the substituent A and B, it should not be similar, C and D should not be similar. However, A and C can be similar or they can be dissimilar. Similarly, D and B can be similar and D and B cannot be similar. So, this type of requirement is required for exhibiting the geometrical isomerism. Apart from alkenes, cycloalkanes also exhibit geometrical isomerism. So, in our previous lecture, we have discussed only that what conditions are required to exhibit the geometrical isomers. Now, in this lecture, we will see the various methods there that is or that are adopted for the nomenclature of geometrical isomerism. Namely, they are cis and trans, Ez, syn and anti system. So, let me change the color so that we can recognize it easily. So, Ez system, syn and anti system and cis and trans system are supposed to be discussed in part 2 of this lecture, and we will focus on the examples, mainly alkenes, coordination complexes and the cycloalkanes. So, we will apply this nomenclature system to alkenes, coordination complexes and the cycloalkanes. Now, if we draw 1,2-dichloroethane by two different structures. Consider it as a A and consider it as a B. In this structure A, the chlorine is present transverse to each other and these two chlorine atoms are present parallel to each other. There is free rotation about the C single bond. Now, this is the question whether these two molecules are representing the same molecule or they are representing the different molecules. Whether the compounds A and B are same or they are different. The two models showing the representing the exactly the same molecule, they are not the isomer. If we see them lookwise, so they are looking different, but they due to this free rotation they can be easily converted into each other. That means they are representing the same molecules. So, they cannot be the same isomers, they are the same molecule, they cannot be, they are not representing the isomers. Carbon carbon double bond are sp2 hybridized. The carbon carbon double bond consists of one sigma bond and one pi bond, and presence of this pi bond locks. What this pi bond is doing? This pi bond is locking the molecule in one position, and therefore, the free rotation around C double bond C is not possible. What basically it is doing? It is locking, the pi bond is locking the molecule in one position and the rotation around C double bond C is not possible. And this restriction of rotation about the carbon carbon double bond is responsible for geometric isomerism. So, we have discussed, we have seen this what double bond is doing. This double bond is restricting the rotation, this pi bond is restricting the rotation and resulting in the geometrical isomerism. We have seen this video in our previous lecture also. Now, let us see it again. So, here we can see easily that the molecule that is looking present at right hand side, it is showing the free rotation, and the molecules that are present at the left hand side, they are showing the restricted rotation. So, thus this restricted rotation is responsible for the existence of the geometrical isomerism. Now, there are two types of isomers, cis and trans. So, which structure we are calling cis and which structure is we are calling trans. So, cis isomer is one in which two similar groups are on the same side of the double bond. So, my dear students, just focus over here this is I am drawing a structure C double bond C. Let us see, I am representing it with the A, B, C and D. Designate this carbon as a 1 and this carbon number 2. For simplicity, divide this structure in two parts. Now, if two substituents similar groups are, say for example, let us have two similar groups A, B, B. So, A are on same side, B are on same side. So, if this type of condition arises, so this type of structures are called cis isomers, and the example is 1,2-dichloroethene. In this structure, it is clearly recognized that 2 hydrogen atoms are present on the same side and the chlorine atoms are present on the same side. So, this type of presence of molecule atoms or substituents resulting in the cis isomers. So, I hope students you must understand what is a cis isomer. Cis isomer is the one in which two similar groups are present on the same side of the double bond. Remember, underline this line, same side of the double bond. Two similar groups are present on the same side of the double bond. The condition is that, again recall, same groups, similar groups, the groups should not be dissimilar. Similar groups are present on the same side of a double bond, then particular isomer is called cis isomer. And what is trans isomer? In trans isomer, the similar groups are present on opposite side of the double bond. Means we can say this two similar groups B B are present on the opposite side and A A are present on the opposite side. Means they are making the structure like X. If the groups are making the arrangement like X, means the structure we are calling it as a trans. So, trans isomer is one in which two similar groups are on the opposite side of the double bond. Remember, opposite side of the double bond. So, two similar groups must be present on the opposite side of the double bond. Let us have an example, 1,2-dichloroethene. In this structure, it can be easily seen that both the hydrogen atoms are present opposite to each other and chlorine are also present on the opposite to each other. Means they are present transverse to each other, they are present in front of each other and opposite side of the double bond. The condition we can consider it as a presence of a X. If the similar groups are making the structure like X, so in that condition we are calling it as a trans isomer. So, and we can see it with the example of some representation. This he can say this chlorine atoms are present opposite to each other and this hydrogen are again opposite to each other. So, it is making the structure like X. So, that is why we are calling it as a trans, but if it see this both the chlorine atoms are present on the same side and both the hydrogen atoms are present on the same side. So, it is known as cis and it is known as the trans. So, means if the substituents are present on the opposite side of the double bond, they are considered as the trans. If they are present on the similar side of the double bond, they are considered as the cis. So, what words are making the difference here is the similar side and opposite side. If they are present on the similar side, we are calling it as a cis. If they are present on the opposite side, we are calling it as a trans. So, I hope you must have understand what is the trans isomer, what is the cis isomer. So, two different spatial arrangement of methyl groups about a double bond in 2-butene. So, let us discuss one more example, 2-butene. 2-butene means say so, it is 2-butene. 1, 2, 3, 4, 2-butene. So, now this 2-butene can be represented in two different types of arrangements. How? See, These two methyl groups are present opposite to each other. These two methyl groups are present on the similar side. 1, 2, 3, 4. Same structure, so I am representing 1, 2, 3, 4. See, in this case, these two methyl groups are present on the same side, and these two methyl groups are present on the opposite side. So, this is making X-like structure. So, by having two different arrangements, this cis-2 butene exists as a cis and as a trans 2 butene. This is one more example apart from 1,2-dichloroethene. So, this is cis isomer, the two methyl groups are arranged on the same side of double bond, whereas in the trans isomer they are present on the opposite side of the double bond. One more example, malic and fumaric acid. There is one more important example here. You can see these two carboxyl groups. Malic acid possesses two carboxyl groups. So, these two carboxyl groups and two hydrogen atoms are present on the similar side of the double bond. But if we talk about the fumaric acid, that is a trans isomer of this malic acid, these two COH group are present opposite to each other, opposite, and these two hydrogens are again present on the opposite side. So, it is making X-like structure. So, cis isomer is malic acid is a cis arrangement and fumaric acid is a trans arrangement. One more example we can discuss here, crotonic acid. So, if crotonic acid again bears COH and methyl on one side and hydrogen atoms on the another side. So, hydrogen atoms are present on the similar side, and in this case hydrogen atoms are present on the opposite side, and methyl group and carboxyl group are again present on the opposite side. So, it is making a structure like X. So, when a structure arrangement like X is present, then again simply we are considering it as a trans. So, crotonic acid exists in two forms, cis and trans. So, cis crotonic acid is called isocrotonic acid, and simply trans crotonic acid is simply considered as the crotonic acid. Again, one more example, allocinamic acid and cinamic acid. In cinamic acid, we are having two substituents again, COH and C6H5. We can represent this structure like this, cinamic acid, CH double bond CH and COOH. This is the structure of ceramic acid. Now, two types of arrangements are possible for this ceramic acid. These C6H5 and COH are present trans to each other, means they are arranged like X, and here they are present on the same side. So, here it is considering as a cis, and cis we are calling allocinamic acid, and we are calling transform as a cinamic acid. Similarly, one more example can be discussed here, oleic acid and aldehyde acid. In oleic acid, this aliphatic chain CH2 CH3 is present on the same side of the double bond, means it is representing the cis form. But in the another structure aldehyde acid, this two alkyl chain are present trans to each other, means it is again satisfying the condition that the presence of X like structure. So, if it is presenting X like structure, we can say that it is transform and that is the cis form. And so, it is how cis and trans isomerism is nomenclature in case of the alkenes. Now, if you look another category, that is coordination complex. So, here we can see that it is exhibited in the diazine and diphosphenes to exhibit cis and trans isomers. So, coordination complexes having a square planar structure or octahedral geometry also displays cis and trans isomerism. Now, what it can be observed that the similar ligands are positioned near each other. If similar atoms, similar substituents are present near to each other, they will be considered as cis. If they are positioned on the opposite in the corresponding trans isomers. So, how we can see here similar atoms amine 9 NH3, they are present near to each other, and chlorine they are present near to each other. It is representing the cis. But if we see here, these two chlorine substituents are present opposite to each other, and this amino group is present again opposite to each other. That means, it is representing the structure like X. So, that is why we are calling it as the trans isomer. So, the condition that is required for cis and trans isomerism coordination complex is the nearness to each other. They must be present near to each other if we are considering as a cis, and they must be present opposite to each other if we are considering them as a trans. Now, apart from coordination compounds, cis trans isomerism also exist in the cyclic compounds. So, like alkenes, cycloalkenes are capable of cis and trans isomerism. A cycloalkane has two distinct faces, and any substituent on the ring lies towards one of the two faces, and when two substituents are on opposite same face, they are calling cis, and if they are present on the opposite face, we are calling them as a trans. So, to just like keep a book in your hand and put two pens, one above the plane and lower the plane, if they are present on the same face, top face, this is the top face, this is bottom face. If see this methyl groups and are present opposite to each other, means one substituent is present facing the top face, one substituent is facing the bottom. So, that condition is called trans, and if they are facing the same, then this is called cis. Here you can see this with this example. In this structure, these bromine substituents are facing the same side, but this bromine atoms are one is above the plane, another is below the plane. So, this is representing these two structures I am representing with the help of some video, just have a look over it. In this video, it can be easily seen that these two bromo substituents are lying above the plane, below the plane. So, if they are present on opposite faces, they are considered as a trans. If they are present on the same face, they are considered as the cis. This is one more example. In this example, both the methyl groups are facing the same, and we are representing them by Vaz bond. So, this is cis. Here this bromo and methyl groups both are, one is represented by Vaz bond, another is represented by Ras bond, means one is facing another plane. So, that is it is representing as a trans. Again it is representing trans and it is representing the cis. So, there are a few examples, one more how to say. So, in this particular case, this will not show geometrical isomerism, this is not the example, but it will show how we have to assign the position with respect to these two substituents. If they are considering these two, it is trans, but if we are considering these two, it is a cis. So, students, you can have a practice by doing these few examples. You can try to identify the orientation, whether they are cis or trans. And this is one more example. Here you can also have practice. This is the structure of testosterone. Here you can recognize whether this OH group, methyl groups or different hydrogen substituents where what type of isomerism they are representing, cis or trans. This is one example that cis trans isomerism present in the medicinal compounds. Chlorprothixene is one more drug that also exists in cis and trans, and there is a vast difference in the biological activity as compared to this isomerism. So, I hope you must have understand this nomenclature of geometrical isomerism. So, in next lecture we will discuss syn, anti, trans and EZ system of the nomenclature. Thank you very much.